data rate, enough bandwidth to accommodate it, I guess. So so we can summarize by saying that increasing the, where is it? So increasing the level of signal may reduce the reliability of the system, because now you're having you're having a higher bit rate, which, as I was pointing out earlier, if the bandwidth is not enough for that particular bit rate, it will just uh, um, create loss of some of the bits in transmission. It's because they're coming too fast. Basically, if something is coming in too fast, reliability of the system can be a challenge. Okay, which means handing it off it will either lead to a higher queue within the next hop system of transmission, which obviously can create a lot of congestion within a particular system. So this is some of the issues that you'd have if you were to be increasing the signal levels. So the higher signal levels would lead to issues like high queuing and higher congestion within the transmission, or at various end devices, or hubs, or end systems, or intermediate systems as well. Okay, so you want to watch out for that when it comes to your noiseless channel transmission. High signal levels reduces the reliability, because then you start having higher bit rates, basically. Now, the other theory that's used to handle the low band channels and band pass channel is the Shannon capacity. So we do also have the Shannon capacity, which also applies to that, and that actually applies to noisy channels. So Nyquist theory is more of the noiseless channel. So if you're dealing with noiseless channels, then you want to look at the Nyquist theory. But when you do have noisy, so there's noiseless and noisy. Noisy channels requires you to basically look at Shannon capacity for noisy channels when it comes to maximum bit rates. Okay, so yeah, so the noise for Shannon capacity redefines the theoretical maximum bit rate for noisy channels. If you do have a medium there where, like, scenarios, so you'd have noisy channels is where you'd have multiple frequencies within a given medium, or within a given wave. There's bound to be noisy. So when you do have that issue, then ideal theory that you want to consider is the Shannon capacity, because that would help you manage your bit rates to guarantee the reliability of the bits being transmitted. And its formula for that is the capacity equals the bandwidth times log base 2 into parenthesis 1 plus the noise or signal noise ratio. So here we're looking at the signal noise ratio as a key element in determining how the capacity of that bit rate is calculated. Okay, so if we look at it from a calculation point, considering an extremely noisy channel, so the very moment you hear noisy channel, you know you're looking at the Shannon capacity theory, in which the value of the signal to noise ratio is almost 0. So obviously telling you that this is almost 0, so you only have 1 to deal with. So 2 raised to the power what value will give you 1? Okay, let me go through first. I'm not even done with the question. I'm trying to answer the question. Let's go through. So consider an extremely noisy channel in which the value of the signal to noise ratio is almost 0. In other words, the noise to signal, so in other words, the noise is so strong that the signal is quite very faint. So for this channel, the capacity is calculated by, if we're to be using the same concept over here. So in other words, with this going by this formula, it would just be B times log base 2 raised to of 1, log base 2 of 1, because noise to signal to noise ratio is 0, so we only have 1, so it's log base 2 of 1, and log base 2 of 1 is 0, right? It's 2 raised to the power 0, that gives you 1, right? So log base 2 of 1 is 0, so 0 times the bandwidth will give you 0. Any number times 0 is 0. So in this sense, the capacity is just 0. Okay? So let's go to the question. So in this question over here, the capacity will be 0, basically. Yeah, exactly. Because, okay, like they pointed out, they're telling you that the XNR, which is the signal to noise ratio, is almost 0. So 0 plus 1, log base 2 of that is obviously 0. So 0 times bandwidth is n hour times 0 is what? 0. So capacity in this sense will be 0 for this particular noisy channel. Another question. So this is a different one. This actually has some value. So we can calculate the theoretical highest bit rate of a regular telephone line. A telephone line normally has a bandwidth of 4 kilohertz. So they tell us a telephone line has a bandwidth of 4 kilohertz. Its signal to noise ratio is usually 3,162. For this noisy channel, what would be the capacity? So going back to the formula, we have a bandwidth of 4. So this is 4,000 hertz, right? It's 4,000 hertz times log base 2 of 1 plus signal to noise ratio. So that will be 3,163, right? So the question is 2 raised to the power what will give you 3,162? So 163 because it's plus 1. And that looks, if you do the math properly, you should get 11.62. I'm just going to my calculator over here. So I'm using a scientific calculator. And I'm trying to figure out what would give me that using some of the scientific, maybe logs and lns to derive or to be able to get that value. And based on my calculation here, I'm getting 2 raised to the power of n equals 3,163 should give me n should be 11.62. So it means that 2 raised to the power 11.62 will give you 3,163. And then you take that and multiply by you take that, you multiply it by um, the bandwidth. bandwidth, right? So in this scenario, so the bandwidth here, let me see, is the bandwidth, no, they didn't use the 4,000 kilohertz. They used 3,000 kilohertz. See, obviously, this side is correct. The log base 2 of 3,163 is 1162. I'm just trying to figure out where the 3,000 is coming from. It should have been 4,000 hertz, right? If I'm not mistaken. Yes, so this is wrong. This is wrong. This should have been, because we had 4,000, so I need to correct that. Okay, this is a typo here. So let me correct that real quick, and then we can easily move on. Let me correct that. So this is 4,000. It's supposed to be 4,000 hertz, because we have 4 kilohertz, which is 4,000. So in that sense, there's supposed to be 4 here. So calculation wise, so what is 4,000 times 11.62? That gives you 46,480 bits per second. So this should be the correct. Yeah, I guess I was still thinking about the 3,000 from the previous question, and that the Nyquist, right, where we had the 3,000 as the frequency, right? Okay, so let me save that as a PDF, so the PDF can also be updated. Okay, while we wait for it to be updated, that's great. Okay, so let me go back to slideshow. Okay, so the answer to this is supposed to be 46,480 bits per second, because the bandwidth was supposed to be 4,000 instead of 3,000. Okay, perfect. So we got that. So we're going to calculate the capacity, right, of this particular question, of this particular um, uh, scenario here that we have. Okay, another scenario. This one is going to involve using. I'm thinking you're going to be using. Okay, let's go through it. So we have a channel with 1 megahertz, which is more or less 1 million, because if kilo is 1000, meg will be another 3 zeros, so make it 1 million, 1 million hertz bandwidth. So it has 1 million hertz bandwidth. The signal to noise ratio for this channel is 63. So they've told us. The question is, what is the appropriate bit rate and signal level? That's a pretty interesting one. Well, generally we've been told what the bandwidth is. We've been given the signal to noise ratio. So we cannot calculate the bit rate directly because of the information that we have over here. So we'd have to apply both theories in order to get to an answer. And we need to get a capacity first. So in this scenario, we have to calculate the Shannon capacity first of the transmission, of the channel transmission first, and that would be 1 million times log base 2 of 1 plus 63, which will be 64. So 2 raised to the power 6 will give you 64, right? Because 2 raised to the power 7 is 128. Okay, so yeah, that's correct. 2 raised to the power 6 will give you that. So log base 2 of 64 is 6. So 6 times 1 million will be what? 6 million. That would give us the capacity, which is more or less 6 megabits per second, or sorry, 6 meg per second. Megabits, yeah, 6 megabits per second, right? Because it's 6 million, which will equate to meg, right? So 6 meg. So that's 6 meg per second. So we're going to calculate the capacity of the channel transmission. Now, from that point, we can calculate the bit rate by plugging that into a Nyquist theory. Yes, that's how we're going to figure out what the bit rate is. So we now, in that case, we have a capacity of a bandwidth capacity, or so a bit rate of oh, sorry. Okay, so the Nyquist, so the Shannon capacity will give us the bit rate, which is the capacity that we found. It's the signal level which becomes the click, because we were given signal to noise ratio. That's why we had to use the Shannon capacity first, so we can be able to derive the bit rate. Great. So the bit rate, or using the Shannon capacity over here, will be 1 megahertz times log base 2 of 64, which is 6 times 1 megahertz, which will end up giving you 6 megabits per second bit rate. Exactly. Now, so to calculate the signal level is where you have to adapt the Nyquist, because the Nyquist is what deals with the signal level, whereas the Shannon deals with the signal to noise ratio. So we go all the way back to, so we do have a bandwidth of 6 megabits per second, right? That's the capacity, or bit rate of 6 megabits per second. Now we need to calculate the signal level. Okay, so if I'm not mistaken, the formula within the Nyquist is 2 times the bandwidth times log base 2 of the signal level, which we have to calculate, right? So to do the calculation, we have to more or less divide 6 megabits per second by um, uh, 2 megahertz, right? And then take log base, and then use the inverse log base 2 of that value to give us the noise, the signal level. So let me see if I can plug in my calculator and see if I can get the answer. Okay, so I do have so the first, okay, so I do have, so the first one we had 6 for the bit rate, which is this one here. We got, oh great, so that's what we had. Okay, so we had 6 meg. I was just about to compute this, and it turns out the the signal level is actually 8. Yeah, so 6 megabits per second divided by 2, inverse log of that. Yes, that's about right. So that's about right. Yes. So when you do divide this, you're gonna get 3. Um, uh, this will cancel out. This will obviously cancel out. So that's 3. 3, 3. The inverse log base 2 of this will give you 8, because 2 raised to the power 3 is what gives you 8. So that will obviously gives you the answer, the signal level. Are we catching on? Because this is how I went about it. So if you take 6 megabits per second divided by 2 megahertz, you're gonna have 3 left, because the megs will cancel out, or the other uh, uh, units will cancel out, leaving only 3. So 3 equals log base 2 of the signal level. So the question is, 2 raised to the power what will give you 8? So we'll give you 3. 2 raised to the power, sorry, 2 raised to the power, um, 2 raised to the power 3 should give you more or less L. So 2 raised to the power 3 gives you 8. So that's where your L comes in. Are we catching on? It's a simple math. If I was writing it out, if I were to type it out on an orderly fashion, you get the flow of it, because we have only 3 on this side over here. So it's 3 equals log base 2 of L. And if you're looking at the log properties, it means that the question is 2 raised to the power 3 should give you L. Right? That's what it means. Or 2 raised to the power what will give you L, which in this case happens to be um, 8, where the n is 3 at this point. Right? That's how the logarithm property works, or attributes works. So 8 is the answer for your signal level, because it's 2 raised to the power 3. That would give you 8, or that will give you the signal levels. Okay, so with that said, we can note that the Shannon capacity gives us the upper limit, while the Nyquist formula tells us how many signal levels we need. Great, wonderful stuff. I don't know whether you're enjoying it, but I seem to be having a good uh, gist of it. especially coming from when you look at it from the calculations and how they apply to the various theories that we have, especially dealing with the uh, low band and band pass transmissions. Okay, now let's move on to transmission impairment. So we're looking at what kind of issues that impair signals or that impairs transmission. So we're going to be looking at distortion, noise attenuations, and what have you. Okay. So signal impairment. Transmission impairment. Transmission impairment, when it comes to signal, is defined as when a signal travels through a transmission media, which are not perfect. So if a signal travels through a medium and the medium is not perfect, then the imperfection causes the signal to impair, to get distorted, or loses its form, its initial forms of transmission. And when that happens, we mean that a signal at the beginning of the medium is not the same as a signal at the end of the medium. So obviously, the imperfection can create this kind of distortion from the initial signal, uh, uh, itself, and the final signal being transmitted. So what is sent is not what is actually basically received. And there are three causes of signal impairment. I keep using signal impairment, which is about the same, but generally we're talking about transmission impairment. Okay? You know what transmission impairment. I don't know why I keep the signal thing is just stuck in my head. It keeps coming up. Okay, so we're looking at transmission impairment. And signal travels through transmission media which are not perfect, and the imperfection causes signal impairment. This means that a signal at the beginning of the medium is not the same as a signal at the end of the medium. And what is basically sent is not the same as what is received. And generally, there are three causes of impairment, and these are attenuation, distortion, and noise. So we'll look at some of the examples of signal distortions, which forms part of the signal impairment, or so which forms part of the transmission impairment. Okay. So yeah, you have the three. So let's pick one of them and look at it. So signal distortion attenuations happens when the original signals get attenuated and the actual signal becomes a bit more inflamed or amplified, and that's what causes attenuation. So when we talk about attenuation, we mean original signal has been amplified either because of the medium imperfection that it's went through, leading to that particular has either more power being applied to it, or some of those theories being applied to them, leading to the original signal taking a different, not necessarily a different shape, but having a higher peak, or becomes much bigger than, has a lot more peak in terms of this amplification than the original information, or than the original transmission. Okay, and when usually that happens, you do have what you call attenuation. For distortion is when an input signal, so here you do have a digital signal, goes through a medium and it just gets distorted. It kind of loses its digital signal form or shape. That's where you do have distortion. And the final one is noise, is when a particular analog signal is transmitted and that there's too much noise within the medium, the the amplitude of the signal the receiving end gets kind of like loses its form. It either have a higher peak or higher amplitude or low amplitude at specific times. So more or less, you have a completely different message being transmitted. And usually when that happens, you do have what you consider noise. Okay? And now when all these happens, performance becomes one of the key issues that gets affected within networking generally. So one important issues that comes up in networking is, as it relates to signal distortion, is performance issues. Okay, it's performance issues, and those relates to bandwidth, throughput, delays, and bandwidth delay products we might have. So yeah, performance obviously, yes, it's one of the key issues that comes across or that gets uh, uh, experienced when you do have signal distortion. Okay, so that's one of the, especially when it comes to networking, performance becomes a huge issue. Okay, and bandwidth, throughput delays, and bandwidth delay products are one of the performance issues that comes up under performance, anyways. As far as performance is concerned, these are some of the uh, key issues that comes up or that needs to be looked at. Throughput is when a number of bits passing through uh, a given medium kind of like gets impeded by a different form of media, in this case a wall passing through an opaque object. And when that happens, the signals can have issues that relates to the how fast the information is actually uh, carried through the medium. So we're looking at transmitting information, and then you do have a barrier or imaginary wall or an impedance, and the time it takes for it to actually go through that impedance, in this case an imaginary wall, is what defines the throughput. Okay, so throughput is the number of bits passing through the wall per given second. So if you do have an imaginary wall or an impedance, it would obviously it would affect the time that each bit takes to get through that particular impedance or that particular barrier that you'd have. So that's what you term as throughput. Propagation time is usually defined as the distance through which the bits transmit, the distance through which the bit takes from time 1 to time 2, but the difference in between, which obviously taken from the finishing time to the minus the initial time will be defined as the propagation time. So in a scenario like this, propagation time will be the distance and in respect to time that it takes for this number of bits to get to this final destination point in reference to its initial time that it started. So the time it took would the difference between the time it took, which is obviously from the ending, for which is obviously the ending minus the initial, will give you the propagation time to that given distance, anyways. Bandwidth delays. Delay product defines the number of bits that can fill a particular link. So if you have a size, a pipe size, the bandwidth delay product is more or less defined as the number of bits that can actually fill out that particular pipe, or in this case, that particular link or transmission medium. Okay, so here we do have the medium, and the number of bits that can fill it up is what you term your bandwidth delay product. Great. So I think that should probably do it for this particular um, uh, session of the for our lecture for today, covering a number of things over here. Right, we did cover a number of stuff. Right, a number of things we covered. Um, Especially at the physical layer, we started with the it was the whole of this lecture was all about looking at uh, the physical layer from a signaling point of view. Okay, from a signaling point of view. Okay, so that was our key focus. In subsequent lectures, we'll look at the other part of it, which is we'll look at the digital transmission part, the other transmission parts, the multiplexing and transmission medias that are involved. Okay, so this was solely the signaling level of the physical layer, and all of this can be found in chapter 3 of the textbook. If there was some stuff that I probably got carried away that you didn't quite get, um, we can go over it during discussion sessions. But do read a textbook so you can get a lot more information on some of those things that you didn't quite get clear. I'm a bit exhausted, so if I skip some stuff or get carried away or was mumbling through some of the stuff, it's probably because I'm a bit exhausted. It's 1 a.m. and I've been talking for over an hour now. So I'm a bit exhausted. Okay, so just bear with me on that. Okay, but yeah, do read chapter 3, and like I said, discussion session we can cover some of the things that I might have either overcovered or undercovered. So at least we can make it clearer to everybody and hopefully get everybody to be on the same page. Okay, folks. All right then, that should do it.